Hi everybody, welcome to Compass. It is my pleasure to introduce Eric Mischell. Eric is a fifth-year PhD candidate in the Department of Atmospheric Science, where he is advised by Dr. Brian Soden. Before coming to the University of Miami, Eric received a Bachelor of Science in Environmental Science from Brown University. While at UM, Eric's research has involved the effect of radiation on the development of mid-latitude cyclones, and more recently, as we'll hear about today, the response of tropical precipitation and the large-scale circulation to global warming. In his spare time, Eric enjoys jogging, reading, and sending postcards.
Wow. Okay, you ready?
Yeah.
Can you hear me? Thank you, Aiden. Today I'm going to be talking about the response of mean and extreme precipitation to global warming, and this is work that I've done in collaboration with my advisor, Dr. Soden. So to begin, I wanted to talk about what we know about the response of the global mean hydrological cycle to global warming. So we expect that the near-surface water vapor concentration will increase by about 7% per degree of warming, in line with the Clausius-Clapeyron equation, and the mean precipitation will increase by about 2% per degree of warming. And Held and Soden, 2006, put forward this equation: P equals mcq, where P is the precipitation, mc is the convective mass flux, and Q is the near-surface water vapor mixing ratio. And they argued that if the precipitation increases at a slower rate than the water vapor mixing ratio, then the convective mass flux must decrease. And since most of in the global average, the convective mass flux is concentrated in the tropics, in the tropical overturning circulation, then consequently the mean tropical overturning circulation is expected to slow down. And this is the verification that Held and Soden provided in that paper, showing that the mean convective mass flux does slow down and does decrease in this model. And so this argument has been widely cited and has stood for 20 years. And so you can imagine that there was a bit of a stir earlier this year when Williams and Givenchy challenged what they referred to as the Held and Soden scaling, that P equals mcq equation, and suggested that when looking at other general circulation models, that perhaps that scaling is not as robust as previously thought. And so we revisited this idea and wanted to see where that P equals mq equation came from, and sort of how it connected to first principles. And so we started by looking at the mass continuity equations for water vapor, cloud liquid water, and precipitation, and the mixing ratios of those three species are given by these Q and subscript terms. And I won't go through every term in these equations, but you can see that the flux terms are inside this divergence operator, and that on the right-hand side we have source and sink terms due to processes like condensation, evaporation, and collision and coalescence form precipitation. And the last term I'll mention is this Vt term, which refers to the terminal fall speed of hydrometeors, and that is process of rain falling out of the atmosphere. And so we assumed steady state and a doubly periodic domain, and we took the spatial and temporal averages of these equations and added them all together so that the terms on the right-hand side all canceled out. And what we were left with was this equation, and all of the terms are derivatives in z. And so we integrated the equation from an arbitrary height c star to the tropopause h. And since these are integrals of derivatives, we're going to evaluate these terms at h and z star.
So there's brackets and bars that like averages, right?
Yeah, that's right. So I forgot to mention that the bracket is the spatial average in x and y, and the bar is the time average. And so this term on the right-hand side is just the precipitation rate evaluated at z star. And if we assume that z star is below the lift and condensation level, below the cloud layer, such that QC evaluated at z star, which is the cloud liquid water mixing ratio, is 0, then what we're left with is this equation. And if the vertical mass flux m equals rho times w, which is the definition of the vertical mass flux, then we're left with the equation P equals the average of m times q. And you can notice that this equation does bear a close resemblance to the original P equals mq equation, except that in that original equation, mc is the convective mass flux, and it's the global average of the convective mass flux times the average of the mixing ratio. Whereas here, in this formulation, it's the average of the overall vertical mass flux, not the convective mass flux, times the mixing ratio, and it's the average of that product, not the individual averages. And so if we divide both sides of the equation by the average of Q, then what we're left with is P divided by Q equals the average of M times Q divided by the average of Q, which is just the mean of the vertical mass flux weighted by the mixing ratio Q. And so we call that ME. And so the final form of the equation is P equals ME times Q. So as you can see, it's very similar to the original, except for in the original, it was the convective mass flux, which just takes the part where the vertical velocity is positive, whereas here, this is the average of the overall vertical mass flux, which includes both updrafts and downdrafts, so W can be positive or negative, but there's different weights based on the mixing ratio. And so this term is positive because where W is greater than 0 are also those areas where the mixing ratio, where it's more humid. And so, and that's where there's rising motion and precipitation. And so we have this new formulation, and we want to evaluate this equation. And so we evaluate it in a cloud resolvent model, CM1, which is in radiative convective equilibrium and has a doubly periodic domain. And in the previous derivation that I showed, we assumed that rho and Q and W could be known at every location, that they were continuous. But of course, in a model, things aren't that simple. And we have a component of the vapor flux that's resolved, which is just rho times W times Q evaluated at each grid point. But there's also a vapor flux that is due to subgrid scale turbulence. And in fact, in CM1, in this configuration of CM1, there's a vapor flux component due to turbulent diffusion, as well as a vapor flux component to the planetary boundary layer scheme. And so these different components of the vapor flux are plotted in these different lines as a function of height, as well as the precipitation rate as a function of height. And so you can recall that we predicted that if our height was lower than the lifting condensation level, below the cloud layer, and this dashed line is the lifting condensation level, the mean lifting condensation level, then we predicted that the precipitation rate would equal that average of rho times W times Q, which is the overall vapor flux, which is the total of the resolved and the two turbulent vapor fluxes. And you can see that when we add these three curves together, below this mean LCL, we get a good prediction of the precipitation rate. And so showing this in a different way, we have ME, which is our humidity-weighted vertical mass flux on the y-axis, versus P divided by Q on the x-axis, and we have three different runs of the CM1 model at three different surface temperatures. And each of these points being plotted is a different level below the cloud layer. And we see that all of these points fall very close to the one-to-one line. And so this confirms that ME does equal P over Q, and this confirms our derivation that we showed earlier. And the other thing that you can see in this figure is that as we increase the surface temperature, then both that mean mass flux as well as P over Q decrease. And so summarizing this first part, which has been about the mean precipitation and circulation, we introduced a new variable, which is the humidity-weighted vertical mass flux, to relate precipitation and water vapor by this equation. And we found that this is a slightly different formulation than that of Held and Soden in their 2006 paper. But the principal conclusion of that paper remains the same, which is if the precipitation increases at a slower rate than water vapor, then the mean mass flux, now weighted by the mixing ratio, must decrease. And so all of this has been about the mean precipitation, but what can we say about extreme precipitation?
Eric,
yes?
Since you just put up a summary slide,
Yeah, sure.
can I ask a question?
Please.
Okay, how does this result relate back to those figures you showed from Williams and Givenchy? Like, does it basically explain their figures, or does it refute them? Like, what's the connection to the work which motivated this new work?
Sure. Yeah, I think that probably the discrepancy that Williams and Givenchy found was they were looking at just the outputted convective mass flux terms, which I think will be slightly different than our kind of humidity-weighted mass flux. I think they should be similar to each other, but at least in a qualitative way. But maybe when you actually quantify it in a model, that's maybe where some of the discrepancies might be apparent. That's my surmise.
The other question I had is, so your reference point is below the subcloud layer.
Yeah.
Right. And once you're below the subcloud layer, I mean, there's no difference, is there, between 1,000 meters, 800 meters, 600 meters? Like why not just use the surface for 10 meters? And if you do that, then it's just evaporation, right?
Well, I think the idea was, sort of in that original Held and Soden paper, they were interested in the mass exchange between the boundary layer and pre-troposphere as kind of, kind of to give a sense of how the, circulation would be responding. And so I think it's useful to look at that interface as
Well, you've chosen a new interface, which is, I think subcloud layer is lower than the boundary layer, right? So.
Yeah, but I guess, I would think that, I guess this is, I don't know, I guess there's no exact reason except for that, this is kind of, a mathematically convenient way to demarcate kind of the two layers.
Okay.
Yeah.
Another question on this. So is the ME going to be less than the MC because this new variable is taking downdrafts into account and other ways of mixing down compared to the convective mass flux?
Yeah, that's probably true. So one thing is the convective mass flux is probably can probably be defined in several different ways, and so in the literature it has been defined in several different ways, and so probably the simplest of those would just be all locations where W vertical velocity is greater than 0, in which case this is including both W greater than 0 and negative W. So I'm not exactly sure. I haven't made a direct comparison between this and the convective mass flux because this is now a weighted average, and I'm not sure exactly how they would compare. But it would be interesting, connected to Dr. Nolan's question, to kind of bring it back to the Williams and Givenchy results, and if I directly compare ME to MC, then I could maybe figure out where that discrepancy comes from. But the difficulty is, as I showed, some of those turbulent vapor flux terms, right, they're not common outputs, so it's hard to look at a large number of GCMs or any model and really evaluate this. So that's why we just pick the one, CM1, and we're able to control the outputs ourselves. Okay. So so this first part of the talk has been about precipitation and circulation in the mean. But what can we say about extreme precipitation? And so there's no predictive theory currently for extreme precipitation, or at least no predictive theory that doesn't rely on some knowledge of the future of the vertical velocity, which is in turn uncertain. And in GCMs, the sensitivity of extreme precipitation, here is a high percentile of daily precipitation in CB5, that sensitivity per degree of warming shows a high degree of model spread, particularly in the tropics. And so in the absence of theory and the ability to use GCMs, we have recourse to the observations. And the good news is that there's a lot of satellites that observe precipitation, and the longest reliable record comes from the Special Sensor Microwave Imager, or SSMI, and that's the instrument that we're going to be looking at. And so this very busy figure, each line is a different satellite that measures precipitation. So as you can see, there's quite a few satellites that measure precipitation. But if we go back in time to 1987, the first satellites producing reliable precipitation estimates come from these F8, F10, F11, and so forth. And these are all satellites that carry the SSMI instrument. And so what can we say about extreme precipitation? So the mean rainfall, R, which is a quantity that we do have a theory for, can be expressed by the following equation. And this is just the expected value of the rainfall. So F of R is the probability density of rainfall occurring with some rain rate R. And this is a way to connect the mean to extreme values or to the change in the distribution. And so what we're going to look at is how the probability of rain events across the precipitation distribution has changed over this satellite period. And so a brief overview of SSMI and its successor, SSMIS. For simplicity, we'll just refer to both of them as SSMI. These instruments have been carried on board several generations of Defense Department satellites, and these are designated F8, F11, F13, and so forth. They form a continuous record from 1987 to the present day. They provide passive microwave retrievals of rainfall only over the ocean, and for our analysis we'll confine it to just to the tropics. And they provide the rain rate P and the total column water vapor Q. And so these plots are showing the mean time series. The first panel showing the rain rate, and the second panel water vapor. The seasonal cycle has been removed, and all of these quantities are shown as a percent departure from the mean. And so, and the different colors represent the different satellites, and so we've included them here to show the consistency of the overlapping time periods of those satellites. So you could see in the first panel, the rain rate increases at a modest but statistically significant rate, and the second panel, water vapor, has a much more pronounced trend. And this third panel is our proxy for the convective intensity, which we define as just the precipitation rate, the rain rate detected by SSMI divided by the column water vapor, and that is calculated point-wise. And so this is kind of a heuristic, but our thinking was that for two locations with the same rain rate, that the location with a less humid environment, a lower column water vapor, would probably have more vigorous rising motion of the air to produce the same rain rate. And so this third panel is showing that convective intensity metric over time, and you can see that there's a decreasing trend, which is in line with the Heldon-Soden idea of a weakening of the mean circulation. And so now we can divide the data into fixed bins by intensity and see how frequently rain events fall into these different bins over time. And so 0 to 30th percentile represents light rain, 30 to 60th percentile more moderate rain, the 60 to 99th percentile moderate to heavy rain, and the 99 to 100th percentile is heavy rain. And so,
Eric, sorry, I gotta ask you some questions. So
yeah, sure.
Go back to the previous figure.
Yep.
So these time series, is that averaged over the planet? Is it from a single point? Is it?
Yeah, sorry. These are averages over the tropical oceans.
Okay, they're averaged over the tropical ocean.
Yeah.
And And so, like, some years, obviously, it's more than others, right?
Yeah, that's
Yeah,
right.
okay. So in the next figure, when you're dividing these into percentiles,
Mhm.
so you're doing them to the tropically integrated rainfall.
It's basically the idea is it's a little bit complicated, but the basic idea is that we basically just take all of the individual pixels of rainfall
Right.
over. If we could do it over the entire period, we would, but instead we just take an individual year
Right.
and basically lay them all out in a line
Right.
from highest to lowest, and that's where we assign our different
Right.
percentiles.
Those individual pixels are different individual locations and individual times. Like,
Yeah, that's right.
Right. So
That's
the point I'm getting at is like, so these figures are completely different. This is the time series of the integrated, like this is a time series of total rain over the whole tropics, right?
Yeah, that's
And
right.
The next figure show, I mean, it's just a different, I'm just trying to point out it's a different thing. It's,
Yeah,
you're
that's
showing
right.
a histogram of rain rates at times and places.
Yeah, that's right. So you're right. This is a mean rainfall. So it's like millimeters per hour, and the following figures are frequency of rain. So it's like, yeah, it's a different quantity. And so what I was probably unsuccessfully trying to get at in the previous slide here was that these are fundamentally different quantities, but they are connected to each other. So the mean time series that I showed is directly connected to how likely rain is to fall in those different bins. So yeah, that is
So we go back to your new figures.
sure.
Right, so, okay, see, those are frequency anomalies in that bin?
Yeah, that's right. So if we have a fixed bin, so say this 99 to 100th percentile. Basically, this is the frequency of events that are basically. Let's say this 99th percentile is 10 millimeters per hour. This is how frequently events are exceeding 10 millimeters per hour over time. So, yeah.
Right,
Thank you. These are again, the trends in frequency of events rather than the magnitude of the events themselves. And so you can see that there's an increasing trend in the frequency of heavy rain and light rain, but this is compensated by a decreasing trend in the frequency of more moderate rain events. And yeah, well,
just a clarifying question.
Yeah.
So 0th percentile, does that mean some positive value?
yeah, that's a good question. Yeah, it's just it's excluding the zeros.
Okay.
Yeah, that's right. Because there are a lot of it's like mostly zeros and then some. And we can do the same analysis, but with our proxy for convective intensity, which was just the rain divided by the column water vapor calculated at each pixel. And again, we have sort of our low intensity convective events and then increasing to our high intensity convective events. And so we see a decreasing frequency in these kind of moderate to high convective events and an increasing frequency of lower intensity events. And then for the highest intensity events, the trend is kind of ambiguous and not statistically significant. And so probably the best way to kind of take in the previous two figures is in these figures here. So this is showing the trend in the frequency of rain events falling into these different fixed percentile bins over time. And so we have sort of the frequency of light rain to heavy rain on the right. And for our observations, which is the blue curve, we see an increase in frequency of heavy rain events and light rain events at the expense of more moderate events. And so when we have that kind of flat mean rainfall curve, we can see that that's a compensation between the increase of heavy and light rain and the decrease of more moderate rain. And we can compare this to similar trends in the CMIP6 historical simulation, and we see that the trends in those models are much more muted compared to the observations. But in general, they do have the right sign of the trend. The sign of the trend sort of matches that of the observations. And this is the equivalent figure, but for the convective intensity measure, and we could see that in general there's a shift between a shift from higher intensity to lower intensity convective events, but the discrepancy lies at these high percentiles. And the reason for that may be several things. So one possibility is that in the observations there are it's difficult to detect the column water vapor in high rain rates, and so we filled in missing data using reanalysis for the water vapor, and so that may be one cause of this discrepancy. Another possibility is that it could be an inherent bias in the CMIP6 models, and so unfortunately there's no clear answer as to which one is right, but at the moment the observations and models by our best estimate give kind of opposing signs of these trends. And so summarizing the second part, we found that heavy rainfall is increasing in frequency while moderate rainfall is decreasing in frequency, and this leads to kind of a modest rise of that overall mean rain. We found that convective events are generally shifting from higher to lower intensities, except for at the highest intensities where the trend is more ambiguous, and that could be due to errors in the observations or to an inherent bias in the models. And the final thing is that the SSMI and SSMIS are valuable tools for analyzing trends in precipitation and convection, and especially valuable because of their long continuous record. And so, it was disappointing to hear that there are plans to discontinue the SSMI program. And so I'll talk briefly about future work. And so our analysis of SSMI was only possible over the ocean because the SSMI can only make accurate passive microwave retrievals over the ocean. And so we wanted to extend this to analyze trends over land, and we were going to use the TRIM and GPM precipitation radars. And of course, what we thought was going to be straightforward is trickier than it appears. And part of that reason is that one of the other benefits of SSMI is there's a long overlapping time period between the satellites. So successive satellites are making measurements for at the same time for a significant period of time, and so we can calibrate measurements to each other. Whereas the overlap for TRIM and GPM is less than a year, and so we're having some difficulty calibrating these two satellites together. And so this will be what I'm working on over the next few months before graduating. So, okay, thank you.
questions? Yeah.
So like for CMIP6, are you using the entire historical runs, or are you using just like the satellite period?
Yeah, that's a good question. Yeah, so it's just matching the satellite period. So just from 1987 to present day, and only over the oceans and the tropics. So it's trying to be as fair a comparison as we can.
John?
Are there any specific systems across the tropical oceans that you see the increase in the extreme precipitation in the extreme, and certainly increase in the very weak precipitation that's associated with MJO or ITCZ, tropical cyclones?
Yeah, that's a good question. So one of the difficulties of using SSMI, so it's polar orbiting satellite, and it kind of makes at most 2 observations per day at any location, and so I don't have the figure showing it, but you can imagine that they're kind of just thin swaths cutting across, and so it's a little bit hard to identify from those snapshots from SSMI what exactly what the systems are, and kind of how they how those systems evolve over time. So based on this analysis, we kind of just treated each pixel from the SSMI data as a rain event, and not concerning ourselves with where exactly it comes from or what broader systems it might be a part of. But of course, that's a really important question. Yeah.
Oh, very nice, lucid talk. Thanks. I'm intrigued by the increasing frequency of your lowest V over Q in there. I'm just trying to imagine what scenarios those are. And it's heterogeneous from 10 to 20. Are these scenes that are very dry? And nowadays, the satellite will detect rainfall that just gets above your zero threshold. And in the old days, maybe the older satellites, or maybe in older times, it would be in the zeros and fall out into the zeros. Have some zeros just gone barely positive, and that's what's going on at the 10th percentile there? Have you tinkered around with your zero top throwing out threshold?
Yeah, that's a good question. I'm not completely sure. My sense is that there's kind of a minimum kind of threshold for that an accurate rainfall measurement is detected. So it seems to be kind of cut off at around 0.01 millimeters per hour, and that's kind of consistent across the different satellites. But it is possible that the newer generations are maybe detecting events that the older ones did not. But I'm not exactly sure how I would tell. The minimums are the same.
Yeah, so similarly with regards to this figure, that spike at the very end, could that almost be reflective of just an increased number of times when you can have higher rain rates due to the rising temperatures and to lesser degree rising precipitation, which is in effect counteracting the overall decrease we see in convective intensity? Does that make sense?
I think so. You mean that there would be maybe? Yeah. Could you rephrase it?
Yeah. So in the CMIP6 models, you have that overarching downward trend, and as you talked about earlier in the presentation, the inverse relationship with convective intensity. But we do see that big spike at the end, both in the rain rate and in the convective activity with the really heavy rain. Could that be simply due to just because this is the percent change in over the decades, could that percent change be spiking at the end simply because the amount of instances where you can get those extreme rainfall events are just increasing to such a degree it's counteracting the decreased effect of convective intensity?
Yeah, so I think it is, you know, I think it is certainly possible that there are these, you know, cases where, you know, for extreme, you know, heavy precipitation events that, you know, our convective intensity measure, or, you know, that vigor of rising air is in fact getting stronger, because that doesn't, you know, just because I think, like you're saying, the mean of that, you know, vertical mass flux is decreasing, that doesn't mean that the extremes will also decrease. So I think it is possible that, you know, for the most, you know, extreme events, that convective intensity could in fact be increasing. But, you know, the fact that we were filling in missing data because with reanalysis, because the SSMI wasn't able to detect the rain rate and column water vapor for those events, that is, like, at least for me, kind of a big caveat, you know, a big question mark, whether this is really a real trend or kind of an artifact of that.
And is that reflected in the rain rate as well, like both of those filled in?
No, so the rain
so
rate.
it's just the convective intensity.
Yeah, right. So the convective intensity is the rain rate divided by the column water vapor. So it can detect the rain rate, but when the rain rate is high, the column water vapor, those are sometimes missing. And so, yeah, that seems to be the case.
Got it. Thank you.
Thank you.
Yeah, this is a comment on the two previous questions, but the this increase in the light rain rate, I'm really gratified to see that, because in the shallow convection community, more of the stratus cumulus is becoming cumulus, and that is associated with slightly higher rain rates. So this is, and we're seeing that in, you know, other observations. So this is consistent with that, and it makes sense. I think as you get a more surface-driven shallow convection under a more stable atmosphere, that you would see that. So really appreciate this talk. Not just for that. It's a nice talk.
Yeah, I think, you know, it's kind of like Sharon's question. You know, it would be great if we could tell, you know, where, you know, where the increase in light rain, if that's in fact associated with, like you're saying, the stratocumulus to cumulus. But yeah, unfortunately, it's all we have is just, you know, rain rate and column water vapor, and so. But it would be great to connect that, you know, through other observations to the cloud morphologies and things like that.
Yeah, thank you, fascinating talk. One of the things that has fascinated me in recent years is the extreme rain that we've seen, for example, in Fort Lauderdale in the last couple of years. You know, we're getting 1,000-year events every other year. And I think some of that may be occurring not in deep convection, but in the boundary layer itself. There are driving north on I-95 in these intense rain events, you notice that there's a very distinct periodicity. So if you drive north on I-95, every mile or mile and a half, you get an incredibly intense downpour, and then it lightens up, and then you get another one. I mean, it's like you're looking at the streamlines rolls in the boundary layer, essentially creating concentrated updrafts, which must condense, I guess, at the base of at that condensing layer that you're using as your separation point. amazing amount of that. And of course, if you go to the Arctic, you also see the bands in the snow over open water that has that kind of structure. Maybe you can comment on that.
Yeah, I think it's a good question. I mean, I think as I alluded to at the end, something we were really interested in is seeing how these trends compare over land, and we are, as you suggest, that heating contrast and that is quite a bit different than what happens over the ocean, and so it would be interesting to compare the two, and I imagine we might see some very different changes over land than over the ocean. So I'll have to let you know.
Any online?
No. All right. Thank you for coming. Thank you, Eric.